So this is another simplified form of S. So S, they have taken a 1 plus beta term as common. So you can also write 1 plus beta into this format. As you can see, this RB by RE value is very, very small. So RB by RE is very, very small. Okay, you can neglect the value when RB by RE is very, very small. Okay, this can be neglected. So when you do that, this RB by RE, I can make it as it is almost zero. So I can ignore the term RB by RE. So when you ignore that term 1 plus beta into 1 by 1 plus beta, so your S value will be equal to 1. So it will be equal to 1. But when this RB by RE value is very, very large, then S value will also become very, very large. So it all depends on how you ensure that the RB by RE value is very, very small when compared to 1. That is the limiting factor in the design of the voltage divider bias. So if RB by RE value is very, very small, then the numerator and denominator terms can be made 0. So in the numerator I have only 1, denominator I have only 1 plus beta. So S will be 1 plus beta into 1 by 1 plus beta. So S will be approximately equal to 1. So stability factor 1 is considered very, very good because it is very, very small. But when this RB by RE value is very, very large, then the stability factor will become 1 plus beta. So it becomes very large. So in the crucial design of voltage divider bias, the RB by RE ratio is going to gain significance because the design and the stability factor completely depends on the value of RB divided by RE. Please understand that. So this improvement in stability factor up to a factor of equal 1 is achieved at the cost of power dissipation. So no other circuit gives a stability factor of 1. Only this voltage divider bias gives the stability factor of 1 among all the biasing circuits and at the cost of power dissipation. I am just adding two resistors R1 and R2. Definitely, when you add resistors, power dissipation will be very, very high. Okay, power dissipation will be very, very high, but at the cost of power dissipation, I am achieving a very good stability factor value which is equal to 1. So to improve the stability, the value equivalent resistance value RB must be decreased. So I told you RB, the approximation what we got there is RB divided by RE is very much less than 1. So if that is the case, the RB value should be less. So if RB value is less, your RB is considered made up of R1 and R2, right? So you have to have more current in the voltage divider of R1 and R2. If RB has to be less, current has to be more because voltage is fixed. Okay, so that is the checkpoint we have here. So improve the stability, the equivalent resistance RB must be decreased so that S becomes equal to 1. When the RB values decrease, the stability factor S becomes equal to 1. But when you are designing that RB value should be as small as possible, the same circuit, you are forcing more current to flow through the resistance R1 and R2. When more current is flowing to the resistance R1 and R2, there will be huge amount of power dissipation, which you cannot avoid in this setup. So, okay, often to prevent the loss of gain due to negative feedback, RE is shunted by capacitance CE. So, to ensure that the power dissipation is minimal, usually parallel to RE, you will have a capacitance CE. Okay, to ensure this, to overcome this loss, we usually add a capacitance in parallel to resistance RE. That is called as bypass capacitance, and the capacitive reactance will be 1/10 of resistance RE at the lowest operating frequency. That is the value how you design the value of capacitor. See, this circuit provides an excellent stability factor, but only drawback is the power dissipation is very, very high because I have huge amount of current flowing through R1 and R2. Okay, huge amount of current flowing through R1 and R2. Huge amount of current flowing through R1 and R2. To overcome that loss, I'm going to connect the capacitance across RE to make up for that loss. And how the capacitance value is designed, they have said the capacitive reactance value should be 1/10 of the value of resistance RE. The capacitance value should be 1/10 of resistance RE at the lowest operating frequency. You know, you're going to design this common emitter as an amplifier, right? So definitely you will be applying signals of all frequency and you'll be finding the output, right? So for that reason only they are saying you add a capacitance C parallel to RE to overcome this loss.